Hi there. Welcome to another exciting session on large language models. Today we are going to talk about fine-tuning a large language models. Have you ever wondered how a general purpose AI like ChatGPT can suddenly become an expert in legal documents or customer reviews? That's the focus of our today's topic, which is a fine-tuning a large language models, that is taking a LLM and then fine tuning it on a specific domain or specific task. So this is going to be a really interesting session. I'm going to break this complex concept into very simple and easy to understand and digest manner. So please stay with me till the end, and I'll also have a demo in the end to showcase entire all the concepts we discussed in this video. So this is going to be our agenda for today's topic. We are going to talk about what is fine tuning, and then we'll see why fine tuning is needed. What is the difference between the prompting, RAG and fine tuning, and benefits of fine tuning, and what is a model pre-training? How do we take the model from pre-training to fine tuning? And one type of fine tuning called instruction based fine tuning, and one type of fine tuning technique called parameter efficient fine tuning, and within that we'll learn about LoRa technique. In the end you will have a fine tuning demo where I will walk you through a real world use case of taking existing LLM and then fine tuning on a specific domain specific data. So and throughout this session I'm going to make this complex concept into very easy way to understand with a lot of examples and analogies. So this is going to be really interesting. Please stay with me, and then we'll uncover the process and benefits of fine tuning LLM. So what is fine tuning is all about? Fine tuning, think like a doctor. You have a general physician doctor who is can treat most of the patients all type of health concerns. But we also have a specialist like a cardiologist, a dermatologist, all right? They are specialized in one particular medical field. That's what the fine tuning is all about. You have a base LLM like GPT or Anthropic or Mistral or DeepSeek. These are general purpose LLMs. They have been trained on pretty much all the data available in the internet. Now we want to take this particular LLM and then train this LLM on a specific domain or maybe for a specific task. You want to train this LLM on a specific domain like a finance or retail or medical, or you want to train this LLM to do a specific task like answering some customer questions or doing a fraud detection for a finance or some answering some medical queries. That means, or it could be that you are having your own enterprise level specific data which you want to train this LLM on. That's what the fine tuning is all about. Okay, now we'll see like what is the benefits of fine tuning, what is the process of fine tuning, some of the technical details of fine tuning. That's what we'll be seeing in the next few slides. So pre-trained models like ChatGPT or GPT or Anthropic or Mistral or DeepSeek are two general purpose. So out of the models are trained on massive internet data, everything from Wikipedia to Reddit to Google, YouTube. That's great for general knowledge, but not ideal for specific tasks. Imagine asking one of these models to generate a legal contract or analyze medical reports. You will get it. It's not that they cannot do it, but the amount of knowledge required, amount of internal knowledge, amount of domain knowledge which you want in that report might be missing. So that's what fine tuning does. Fine tuning adapts to a specific domain. So fine tuning let us steer the model towards a specific industry. For example, if you want to fine tune on say 10K filings of all the companies in the US, suddenly the model understand the financial terminology, and then the is better than a general purpose model. It is like a giving a general doctor, as I told, a specialized training in cardiology. So how does it improve? It improves accuracy and niche tasks. You will also see performance gems and tasks that aren't well covered in general training data, like reviewing a cybersecurity incident report or diagnosing issues in industrial IoT logs. So fine-tuning teaches the model the patterns and language it wouldn't learn from casual web data, and it enables alignment with the company data. You can fine tune a model on your internal customer service logs, product names, and any specific compliances which are very specific to your industry. Now the AI speaks your company language, literally. Maybe for example, you want to enable your customer support with some of the policies of your company. So you want to train your LLM on specific knowledge which is very internal to you. And another important part is that LLMs are hallucinate all the times. So general model tend to bluff when they don't know something. But with fine tuning, especially on reliable data, the model learns to be more grounded. Think of it like training a new employee. They stop guessing once they have seen enough real example. And this is essential for enterprise grade AI performance. End of the day, enterprises needs models that are accurate, secure, and aligned with business goals. At the same time, they also need a performance efficient models. Fine tuning is what takes us from a cool demo to a production ready solution. It's the difference between a chat GPT and a domain expert bot. So there are different ways to steer a general purpose LLM to do a task for a specific to your domain, like a finance or retailer, banking or medical. So one of the technique is like we will explore this prompting, RAG, and fine tuning. Prompting is like someone is acting like just to give a simple analogy, it's like acting like a doctor. You say to the model, you act like a doctor and answer me this question. It might do most of the time, but it might fall short of the details which is required for to answer the query. And again, in this case of a RAG, which is retrieval augment generation, what you are doing is you are augmenting that LLM with the knowledge which is internal to you. So you are building a database of data like a vector database, and then for that particular user specific question, you are getting the data from that database and then giving it to LLM as a context. While this was great, but it may not be, lot of times you might get the data which is not relevant to the context depending upon how you store and chunk the data. The next one is fine tuning. It is like you are actually a specially trained doctor instead of a doctor which Googles and then gives information. That's the difference between a prompting, RAG, and then fine tuning. Now let's get into some more details of this. So first we have prompting. This is the simplest method and then very fast. So we write a clear prompt to get the models behave the way we want. We are not changing the model itself, we are changing the model a good instructions to use this when you need a quick answer based on general knowledge, like summarizing a new article or answering a specific question or writing a story, right? The big advantage is that it's fast and don't require any special setup. You just need to make sure that you write a very clear prompt with the clear instructions. But the downside is that it is a very shallow. If a task is too specific to a particular domain or particular task, and if accuracy really matters, the model might fall short or sometimes make up things or miss the mark. The next one is RAG, which is retrieval augmented generation. Next we have RAG, which this model doesn't just generate answers from what it knows, it first retrieves document from a search system and use as a context. So what we do in RAG, we take a domain, a data which is very specific to your organization need, and then chunk it, store it in a vector database, And then when user asks a question, we do a semantic search. That is, we retrieve the chunks or data which is relevant to this particular user question, and then pass it as a context to LLM along with the prompt, so that LLM can answer the question with that prompt. Again, this is has got some limitations. you know this is ideal when your data changes frequency, like customer FAQs or news or legal rules, and you want the model to stay grounded in real sources. This is good, but the downside is that lot of times these vector databases, when they do semantic search, might get the data which is not irrelevant to the user question also, and model might give you the answer which is not so accurate, right? The And then it is also very technically complex to build the vector databases, embedding, retrieval logic, and all of that has to all work together. So by chance, if a wrong document retrieved, the model answer might still be off. Our next strategy is fine tuning, right? So this is the most powerful approach. So you are literally training the model on your own example. So it learns your domain, it learns the tone, it learns the task for your need. So fine tuning is perfect when you need the model to perform very specific job, like analyzing the contract, writing in your brand voice, like you are having your own terminology, your own jargons, your own brand information. You want the model to talk in that, or answering with a high precision. The benefit is high accuracy, and it learns the patterns deeply. But again, it is not doesn't it also has got some drawbacks, right? This is very time consuming and resource intensive. You need to train to fine tune the model. You require a lot of computing power, a lot of GPUs. You need to also label the data, and if any changes in the data, means again retrain the data model, which again adds to additional cost in terms of computing resources. So to summarize, if you want very fast, flexible solution which write with the LLM, prompting. If you want things which is data changing frequently and you want to keep the model up to date with all the changes happening with your data, then RAG. And fine tuning is when you want the precision, the accuracy is very high, and then you want to have the model to talk in your own general, with your own curated internal data. Sometimes we can use mix of all these three approaches. You could take a fine-tuned model and then actually use a RAG with the real-time information with a good prompting, right? So this is a mix and match, but I'm just trying to highlight what is the difference between a prompting versus a RAG versus fine-tuning. This is very important to understand before we choose which strategy we need to adopt for our specific business need. So let's talk about what you actually gain when you fine tune a model. Beyond just some cool technical factors, we look at 4 different areas of benefits, like performance, privacy, cost, and reliability. So performance, right? First, the fine-tuned model deliver much better performance on a specific task. So imagine a general model trying to summarize a legal contract. It might merge some key clauses or get the tone wrong. But a fine-tuned model trained on thousands of legal docs will nail it because it understands the structure, language, and intent behind this document. Say you are an immigration attorney and you want to actually have a model which will adapt to the various clauses and section related to immigration. A model which is fine-tuned on a immigration law will actually perform better than a general purpose model. Same goes like finance or healthcare or customer service. You got an expert level performance. Next one is the data privacy. When you fine tune using internal data, the data stays secure within your environment. You are not sending your sensitive data to external API like OpenAI, Anthropic. This is a big deal for a lot of companies in the regulated industries like banks, hospitals, insurance. You can stay compliant and in control. You are not sending any of your data outside of your network. The third one, cost efficiency. You might think fine tuning is expensive initially to start with. Yes, the training can be expensive because of the lot of computing power involved. But at inference time, it often saves you money. Why? Because a smaller fine-tuned model can do the same job without massive prompts or external search system, vector databases, a lot of engineering effort to build all that plumbing work connecting this, retrieving the data, getting the context and passing it to LLM. So this means you are actually having a fewer tokens. Like when there is a less tokens, you're getting a faster response time and less computing time power. And finally, reliability. So fine-tuned model makes fewer hallucination because they have seen the real examples from your domain. They learn how your data works, what tone to use, what mistakes to avoid. That means more predictable behavior, more trust in your AI output, which is very critical for anything customer facing or any decision driven. So long story short, fine tuning gives you expert level performance, a privacy by design, and a low long term cost, and more importantly, the confidence in your results. So it's not always the first step, but when the precision matters, it's often the right step. Now let's talk about what is model pre-training. This is very essential to understand before we understand the fine tuning. We want to understand how an LLM like GPT or Anthropic or they have been trained. So before a language model like a GPT or a Llama or Mistral can do anything useful, like answering questions or writing emails, it has to go through a process called pre-training. This is the foundation of everything. So pre-training is a very first stage in building a large language model. It happens before any fine-tuning or customization. In this stage, the model is fed with a huge amount of unlabeled text data, meaning we don't tell what the data means or how it interprets, it learns on its own. The data can come from wide range of sources like things like books, Wikipedia, websites, open source code, Reddit, conversations and more. Basically anything which is publicly available within the language. So how it is done? It is again done using your training your neural networks. Basically it just goes through the training. It tries to predict the next word and then the word is wrong. It learns, it adjusts its weights, it biases. The whole mechanism of training that model, it learns. So the goal here is to help the model to learn the basic language like grammar, vocabulary, sentence structure, the facts, something historical facts and reasoning patterns. Basically we're giving the model a broad based education. So by end of this model has got understanding of language, but it doesn't know how to perform a specific task like say summarizing a legal text. It might know to a greater extent, but not to the precision accuracy you want because it has been trained in general legal language rather than a specific immigration law or specific contract law. So we are just teaching the model just like training a person to read and write in general before you teach them a medicine or law. Now let's look under the hood and talk about how pre-training actually works behind the scenes. So pre-training uses a method called self-supervised learning. This means that model learns the patterns in data without needing human labeled answers. The model is given a sentence like say the cat sat on the, okay. Now it learns to predict the next word, okay, or shown a massive sentence and to learn to fill in the blanks. The training happens on trillions of tokens literally. So what is a token? A token is basically a word or a piece of word. This process can take anywhere from weeks to months to complete, and it requires huge amount of computing power to basically depending upon the model size. And then think like, you need to have a huge cluster of GPUs, thousands of processors, and massive power usage. That's why only very big companies can afford to train an LLM like on the scratch data. The result is a general purpose language model. It can read, it can write, it can reason, but it doesn't know your company data or your specific task. This pre-trained model becomes a starting point for all downstream tasks like a fine tuning or a prompt engineering or a RAG. It is like, uh, a college grad who is ready for a job. Now we can teach your own, company's, job to a college grad. Now we go from a pre-training to fine tuning. This is again like a generalist doctor becoming a specialist like a cardiologist. We'll see what is the process of actually making this pre-training model to a fine tuning model. So let's take fine tuning one step further with something called instruction based fine tuning. This approach is about teaching model to follow instructions the way human would, not just complete a sentence but perform a task like summarize this text or classify sentiment of the review. You are fine tuning based for a specific task on a specific domain. For example, you are having all the reviews, you want to find the sentiment of the review, right? Then you will fine tune your instructions include classify the sentiment of the review. uh, Instead of random text, we give the model carefully curated examples that pair a clear instruction with a desired response. We'll see the how we form instruction in the coming demo, but we are going to make an instruction data set. These are data set where model sees thousands of tasks written in natural language and learn to complete them correctly. So the beauty of this model is generalizations. Once a model sees enough diverse instructions, it can handle new one even it hasn't seen before. That's why instruction tuned models are used in almost every chatbot you see today. Even a GPT-3 becoming a chat GPT is nothing but an instruction based fine tuning. So in short, instruction fine tuning is what takes general language model and teaches it to be helpful and then task focus like your own a personal assistant. Now, when I say from raw data to instruction format, here's one example. Say my raw data are having a customer review. The food was cold and service was slow, not coming back. So we have labeled the data as negative. Now I convert this into an instruction. What is instruction? Classify the sentiment of the following review. This is the input, this is the response. Now the model knows that an instruction of type classifying a sentiment and this type of input means negative. So now you are taking the raw data, you are converting to instruction, a specific instruction like classifying a sentiment. It could also be something like, summarizing a text or answering a question. Okay, answer the below question, and then this is the input, this is the answer, right? So you are actually converting this raw data into instruction, and the model is fine tuned on this specific instructions. So what this does is it enables the model to learn different tasks like answering questions, summarizing some text, or maybe doing classification. So this is where you make a training data, a general purpose data, into an instruction aware type of data. Now let's understand what is the process of this instruction based fine tuning, how it works under the hood. So we start with a specialized instruction data set. So each example has been clearly written input like, I know for example, this is a review and the sentiment of this review is negative. Sentiment of this review is positive. This is a question and this is the answer. So these are the data which has been already curated, collected. So these examples are collected from, maybe it could be some human written task or generated, or maybe of course a lot of data engineering effort has been gone into before we arrive at this data. Next, we tokenize and format this data to fit in the model's input format. So I'm going to talk about this these steps when we actually walk through the code. I'm going to explain about what is the tokenization, why we are tokenized data. We get details later when we actually start the code walkthrough. So this step turns the instructions output into a sequence of tokens the model can learn from. Then we feed these tokens to a pre-trained language model, one that is already understands general language but hasn't yet learned how to follow tasks. Now comes actual fine-tuning step. The model go through the thousands of instruction response phase and adjusts its weights using a gradient descent, meaning the difference between its output and the correct answer. At the end of this process, you have an instruction following model, one that not only knows how to use a language, but knows how to do the things with the language, like answering questions, summarizing documents, classifying text, and maybe any other task which it has been specifically trained on. So now let's talk about some of the techniques in fine tuning a model. One of the technique is called parameter efficient fine tuning. So just to think like this, let's say we built a really smart robot named Llama. It has been trained on tons of knowledge, science, books, even bit of cooking. Now we want Llama to help with something specific, like understanding restaurant reviews. Normally, to teach the new skills, we would have to retrain the entire model from scratch. But that's like asking Llama to go back to school for years just to learn one topic. Instead, we use a clever shortcut called parameter efficient fine tuning called PEFT. Okay. So with this, we don't change the whole brain. We just add a small specific task to upgrade. So think of it giving like a llama a new chip that helps with the food reviews while keeping the rest of the knowledge intact. So this is the heart of performant efficient fine tuning. So we'll go into some more technical aspects of this in the coming slides. So basically what it means is that you train just few parts of the model, leave the rest frozen and teach with the new skills efficiently. So to get into some technical details of the PEFT, what happens is we actually have an existing model. So what we are going to do as a first step, we are going to freeze the existing model's layers. So we are not going to touch them. Instead, we are going to add a new layers, okay, and then train these small adapter layers, which might be just 1% of total parameters. That means it is faster, cheaper, and way more resource efficient. So you still get this great performance, sometimes nearly as good as a full fine tuning, especially when you are working with domain specific data. There are different PEF techniques like adapters, LoRa or prefix tuning. So we are going to talk about a technique called LoRa, and that is what the final demo is also going to be, like where I'm going to walk you through how to take an existing LLM and then fine tune on a specific financial domain data. Now let's zoom into how PEFT actually work and introduce a special technique called LoRa. So inside this LLM brain are layers of math called linear layers. These use big weight matrices named W to process input and make decisions. Normally when you fine tune a model, we update W, but W is huge, millions of numbers. So instead of doing that, LoRa says, let's freeze W and just add a small correction to it. It's like giving LLM a translator headset. Instead of reprogramming its whole brain, we keep the original W and add a tiny change to it. This change is called delta W. So the new weight becomes W plus delta W. This is like a layering a new knowledge on top without disturbing what is already there. So I'm going to talk more about the LoRa technical concepts when we have the code walkthrough. But let's understand the concept in general sense, right? How LoRa actually builds a tiny update to the model. So instead of learning a full matrix or delta W, which could be still be large, LoRa breaks it down into two very small matrices called A and B. First, let me give an analogy before getting some technical details. Say for example, you want to draw a big picture or draw something big on a canvas, right? So you have a huge canvas where you want to paint a big picture. So you don't start on the big picture. First, you draw your idea in a small paper. You first draw the idea, how the picture has to look, what color has to be there, how is the placement, what is the background, the contrast. You work out all things in a small paper and then say you draw it on a very big canvas. That is what LoRa is all about. So the two matrices I'm calling A and B does same thing. So this basically trick is coming from something called a low rank approximation from a linear algebra. So what does A and B? It takes the input and compresses input. It shrinks it down into a smaller space, and then B expand it back. It stretches into the original size. It's like give another analogy. It's like a folding a note and then unfolding it, but only learning the folds. So during the training, the model uses output is equal to this weight into input plus this matrices B into the matrices A into input. So if you see that equation, the first part W into input is the original model response. The second part where you are having A and B matrices into input is our tiny task specific correction. And best of all, we only trained A and B. W is still frozen. So training is fast, memory efficient, and the original model stays stable. And you have different ways to the fine tune. There are different levels of fine tuning. At the bottom of the pyramid, if you see, we can use something like a PyTorch or TensorFlow where you have a full control, but you do everything on your own, right? It requires a complex setup. You should have a really, good working knowledge of PyTorch, TensorFlow, because actually you can do that. Or we can use some frameworks and libraries which are flexible, user friendly. You still need to do some amount of, heavy lifting. Another one is a simplified interface which is low code like Lamini or Onslaught, even SageMaker or Vertex AI. This gives you APIs, a higher level abstraction where, for example, with Lamini, you can just with 3 lines of code, you can fine tune entire model with just 3 lines of code, right? It is that easier. You don't have to learn about all the frameworks, libraries, PyTorch, everything. You have a model, you know how to build your instruction data set. Now I give it to Lamini, or maybe you can use SageMaker, Jumpstart, like all these tools which will help you to fine tune an existing model easily without having to invest so much time and effort in building that model. But of course, they are not flexible like PyTorch or other frameworks, but they are very fast, easy to get started with. Okay, now I'm going to walk you through a step-by-step approach of fine-tuning a model. So we are taking a LLM, a small lightweight LLM with 70 million parameters like Pythia. The reason being, you can take a big LLM, but you require a lot of computing power, you require a lot of GPUs. I was trying to do this fine-tuning within the CPU, so I have taken a small model. But of course, the process remains exactly same. Even if you take a big, a 7 billion parameter model, a 100 billion parameter model, you still need to go through the same process of training. It's just that it's all about the computing power required. So to start with, we need to inform all these libraries. The libraries like transformers gives us the tokenizer and model loader, and then PEFT gives us a LoRa specific configuration utilities. And TRL, which is short for transformer reinforcement learning, gives us a SFT trainer, a high level trainer made for instruction, tuning task chartboards. And then the data set from Hugging Face data sets where we can get the, actual data sets which are available. So the step 2 is load and explore the data set. If you can go to Hugging Face, you actually have lot of data sets available like this. You can actually use them as it is. They are all curated, they have, for example, I'm taking this financial QA 10K data, which has got all the 10K data from different companies, like you can see like Nvidia, Tesla, like a lot of host of companies, Apple. It is having the data from all the companies. So what it means is that I'll be training my model now, get a good understanding of various companies, their risk factors, the domains and everything. So I have taken this 10K, financial QA 10K data. So anytime if you take any data, the first thing you do is you need to explore the data. You need to first understand what is the data, what columns are present, what is average question length. So by the way, I'm not going to run each cell here, because typically if you want to fine tune a model, the whole fine tuning process takes more than an hour. Okay, so I have already fine tuned the model. I have the results. I'm going to walk you through the code and then what is the eventual outcome of each cell. So basically this is what my data is. I just print some 3 sample examples as I shown. The same thing what I have shown here. I'm trying to understand what is average question length. Basically I'm just trying to get a sneak peek into my data set. Okay, the next one is, as I told, we need to convert this raw data into an instruction format, which is for a instruction based fine tuning. So what we are trying to do now, the data is like this, right? Like you have a question, you got an answer, you got a question, you got an answer. Now I'm converting this question answer into this format where I'm saying instruction. So what are this one, and this has to be your response. If this is the instruction, this has to be your response. So I'm actually converting this into instruction based fine tuning, so that when I instruction based data set, so that when I can fine tune the model, it knows that okay, yeah, the instruction is this, I have to respond like this. So you also have an option to upload this data set back to Hugging Face so that you can reuse it anytime. In fact, if you want reuse, you can actually take the data set from here. I actually uploaded my instruction data set into Hugging Face, so that even if anytime I want to, I don't have to redo it again, or anyone wants to do, they can just take this and then fine tune the model on their model, right? So the next process is tokenization. So basically what is tokenization? So every LLM can learn the text, but the text must be converted into a numbers. So this process, just to simplify, basically converting the text into numbers, this process is called tokenization. So for example, if you have something like a financial report, this financial report becomes something like this, right? So something like this. So basically a token is usually a chunk of text, as word or subword, but again there's a lot of techniques of tokenization. We are not going to all those details. All you should understand right now is that we are actually tokenizing this data. To tokenize, there is a library from Hugging Face, Hugging Face transformers, something called auto tokenizer. So and every model you choose has got a different way to tokenize the data. Like 1, 2, 3, 4, it could be meaning a financial in this model, but it could mean a different word in another LLM you choose. So this auto tokenizer model gives you the tokenizer for a specific model you are trying to fine tune. So in this case, I have taken this Pythia 410 million model. I'm going to fine tune on this model. Now I'm asking auto tokenizer, give me the tokenizer for this model, right? And then I'm going to tokenize, but I'm going to keep, when I tokenize the data, I need to have what is the max length. And then there is something called padding. Padding means is that if the text is too short, for example, you have something called one sentence, one cell line is having only the finance, okay, nothing is there, but it is not meeting your the character maximum length. So instead of leaving it blank, you want to make every tokens of same length, you add some zeros to the end, so that you actually tokenize, you have the consistent length of each token. So if you can see here an example, So for example, this is a question, right? This is my instruction, what in NVIDIA initially focus on something, and then there is a context. Now this has been converted into a tokens like this. Now you can see I have added some zeros, some kind of a padding happened because we want to achieve that the length, right? So this is called a tokenization. You are actually converting a text into the numbers. So this is the process of tokenization, which is very important step. So once you have the tokenization, so to recap, you have the data set. You converted the data set into an instruction based format. Then you tokenize the data set so that the model can understand from it. So next, the step number 5 is that we need to have the LoRa configuration and then training argument setup. So some of the important, for example, most important part is that rank here. As I told, this is a low rank dimension. What is the dimension of the low rank? We talked about this low rank, right? Basically, if you want to paint a bigger picture, you are actually having a smaller picture drawn on that, right? So imagine again you are trying to create it using say 8 crayons instead of 64, right? So these 8 crayons what you are using to make a small picture is your rank, right? So it could be and this is the rank of the low rank matrices we want insert. So think of it as like a number of neurons in your lightweight adapter. More means better capacity, but more also means more memory, right? And then we are having LoRa alpha, which is scaling factor. So this scales the output of adapter layer, controlling how strong the adapter signal has to be. And the target modules, these are the layers we will modify, and this will change based on your model. So to know like what modules are there in your model, okay? For example, for me, before I fine tune this model to understand what are the layers on my module, I actually ran some maybe I lost it here. I ran some code which would tell me, yeah, this model is having these are the layers in my model. So I need to first understand those target modules, the layers in the module, before you actually can actually go on. Then I can come and specify the target modules here. The next one is the LoRa dropout. So we apply something like a 5% dropout to LoRa to update our for the regularization purpose. So and bias is equal to none. We are not touching the biases of existing model. And then next one is a task type, which is a casual LLM. This tells the PEFT that we are working with an auto-regressive models like ChatGPT or Llama. Again, I would also encourage you to go back and learn some of this deep learning concepts, which are very essential if you are actually doing with the libraries like this, or if you are doing something like a Lamini. Okay, you don't do all these things. You just give the Lamini the model, and Lamini takes care of doing all the settings. Maybe, but the reason I choose this approach is better to understand what are the different parameters or configurations which will actually impact your fine tuning. Right now, once you have this LoRa configurations where you defined basically the most important configuration I see in this is the rank, okay, and then this target modules, and then this the scaling factor, and then yeah, rest everything you can more or less keep as default values. And then we also have a training arguments like where you want to save, and then what is the batch size and number of epochs you want to have, and then what is saving strategy. So whether you want to push it to hub after everything is done. So this is basically a step 5, a LoRa configuration, which is a very important step, because the configuration you set in the step actually determines how better your fine tuning is going to be, right? So once you are done with this, what you do is you actually start fine tuning your model, you first load your pre-trained model, the base model, and then you apply, you get this PEFT model based on your PEFT configuration, and then you use an SF trainer. To the SF trainer you pass a base model, you pass the training arguments and the tokenized data set. So we are passing the base model, which is in our case Pythia 14 million model, and then this arguments, this is the training arguments which I have the LoRa configuration, everything, and our tokenized data set, and we say train. This would typically takes, depending upon their model, anywhere from, if it is a small model like this, it may take 30 minutes. If it is like something like a llama, a 7 billion model, it might take 2 hours, or it can be, if it is something like a really big model, it may take a few hours to days also, right? So once this is done, then you have an option to save in your local directory, or you can also push it to Hugging Face. For example, in my case, I have actually pushed this model to Hugging Face. So even if you want to reuse this model as it is, you can actually go to Hugging Face, and then using this path you can actually get this this is now a fine-tuned model. The Pythia Financial LoRa is a model which is fine-tuned on the 10K data from all the SAC filings, right? Now we are ready to test our understanding, whether we want to test whether the fine-tuning works. So now what I do is, to show you the difference, I compared before and after. Before fine-tuning, for the same question, what is the output? After fine-tuning, for the same question, what is the output? So for example, the question I have asked is, what are Tesla's main risk factors? Now this is my the base model, where I put all the temperature, the max tokens, max how many tokens you want to have, what is the temperature of the model, and then and then this is for the new fine-tuned model. So I use, if you see, I use exactly same parameters, both the tokens, the temperatures and everything for both the base and this model. We are having the same prompt, same question. Now we'll see, if you see before fine-tuning for the question, it includes other, it gave very generic answer, but after fine-tuning it is telling you the answers which are from the 10K filing. You could see that this is very elaborative answer for the same question, what all the Tesla's main risk factor, because this information is coming from Tesla's 10K filing. That's why your model is now a domain expert on the 10K filings of every company. Now you can give this model, ask about Nvidia, you can ask about Tesla, you can ask about Google, Amazon, any company you want. It will give you their the risk factors or any other information which is there in the 10K filing with this model. So this is what the power of fine tuning, where it brings that domain expertise into your model, right? And then finally I want to show you like what all the the new A and B matrices, what I was talking LoRa, which is added to the model. If you want to see them, you can just print here. You can see that these are different layers. If you understand like K, V, Q values at matrices in deep learning in attention mechanism, you will understand this better. But I would also encourage you to, before you actually fine tune the model, understand, get a good understanding of a deep learning concepts, and then which is very essential before you actually start fine tuning a model. Okay, that brings us to the end of this fine tuning session. Hope you enjoyed the session. I'm also leaving the GitHub repo for this notebook in the comment section. Please feel free to ask any questions, comment, and I see you in another session next time. Thank you.